Hello everyone, and welcome to this video about ratios and proportions and the teaching of these ideas in later elementary school. This video is largely based upon Chapter 17 in the 10th edition of Elementary and Middle School Mathematics, Teaching Developmentally, written by John A. Vanderwall, Karen Karp, and Jennifer Bay Williams. Well, as we begin to explore these ideas of ratios and proportions, I want to start with a video that we can maybe appreciate here as teachers here about going on a bad date and how this can apply to ratios. So let's begin our conversation with this video today. I'm going to go ahead and pull it up. It's from a website called Math Snacks.
What are you going to order?
I don't know. The fish looks good.
I don't like fish. I was fishing off the coast of Alaska when Dog jumped in the water and he was all wet. It reminded me of the song about a man whose dog dies and his truck stops working, and there was something about a train. Even though my dog didn't die and I don't have a truck because I was on a boat, but it made me really sad. So once I listened to it backwards to see if the truck would start working, the dog didn't die, but it just sounded weird and I was still sad. Do you ever listen to country music backwards?
What are you even talking about?
Fish. I'm talking about fish because it reminds me of when my dog died, like that movie that had that guy in it from the other movie that was hilarious, remember? It was about space and there was the woman with the blue hair. I laughed so hard milk came out of my nose.
Oh, my phone is ringing.
I don't hear a phone.
No, really, I have to take this. That entire time, I spoke 25 words to his 175. That means for every one word I spoke, he spoke 7 words. He spoke 7 times as much as I did. 7 times. It was like me, talk, him, talk, 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 talk. Me, talk, him, talk, 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 talk. So, do you like fish?
Don't like fish.
I asked the last guy I dated about fish, and he rambled on about trucks all night. Have you ever dated someone who talks too much?
Can't trust fish.
My phone is ringing. That entire time, I spoke 36 words to his 6. For every 6 words I spoke, he only spoke 1 word. I spoke 6 times as much as he did. 6 times. It was like me. Talk, 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 talk. Him. Talk. All I want is a guy that can talk with me on a 1-to-1 ratio. So, do you like fish?
I don't like fish. My roommate does, though. Do you like fish?
I do like fish. Gosh, I've been on some bad dates lately.
Funny. My roommate says the same thing.
Do your dates talk about fish?
Not really. Do yours?
One date talked about fish, had a truck, and listened to country music backwards.
My roommate talks about fish, has a truck, and listens to country music backwards.
I think I dated your roommate. Have you noticed we talk about the same amount? A 1-to-1 ratio.
Indeed, we do talk about the same amount. A 1-to-1 ratio. Bread.
All right. Well, kind of a fun little video to begin our video lecture with, but it has to look at an interesting way of thinking about ratios, comparing 2 quantities. In this case, the amount of words spoken by the lady in the story and the other number by the men in the story. And it gives us an interesting way to analyze the type of conversations that they are having. Well, when we think about this topic of ratios and proportions, when kids hit grade 6 in the Common Core standards, this becomes an entire domain in of itself and becomes a very large focus starting in 6th grade. It doesn't mean the ideas aren't previously encountered with multiplicative comparisons in grade 4 and other types of relationships in grade 5, but specifically the language and emphasis begins in grade 6. One of the very first standards that we see in grade 6 reads the following: understand the concept of a ratio and use ratio language to describe a ratio relationship between 2 quantities. For example, the ratio of wings to beaks in the birdhouse at the zoo was 2-to-1, because for every 2 wings there was 1 beak. And for every vote candidate A received, candidate C received nearly 3 votes. So there's a little bit of a language to ratios and some different ways of thinking about it. And let's explore this more. So first of all, again, we're talking about a ratio being something that relates to quantities or measures within a given situation. We've already seen the example in the dating talk, but it could be many different types of scenarios. We might say 3 out of 5 people prefer McDonald's. And as a reminder, ratios can be written the same way we wrote fractions, like the 3 over 5. It can also be written with a colon, like 3 to 5, and even 3 out of 5 using language. It may also sound like this. For every 2 people that like cats, there are 3 that like dogs. And again, there's many ways to properly write a ratio as seen on the screen. Now obviously, as we talk about ratios, this has become after years of talking about fractions. And obviously they are related. Ratios and fractions have a lot of overlap. But it's important to note that not all ratios are fractions and operate as such. And so we'll talk about that a bit in this video as well. So let's give you a little quiz here. So here are 7 situations. I want you to pause the video and jot down which of these scenarios do you think represent ratios and which do not. Okay, pause the screen. Okay, let's see how you did. Well, it ends up that all of them are ratios except C and E. C and E are not ratios because these are not comparing 2 different quantities. They're really just a fraction of a whole, 1/3 of a donut or 3/8 of a mile. Again, they are fractions. They are a part of a whole we're thinking about, but again, it's not comparing 2 distinct quantities. When the other ones, they are, but it may not be obvious at first. For example, in B, it says the odds of picking a heart are 1 to 3. What are we comparing? Well, there's 4 suits to a card, so for every 1 heart, there are 3 other cards, spades, clubs, and diamonds. We're comparing the suits of the cards. In D, you might say, but Adam, there's only one number there, 64 miles per hour. But again, in a rate like that, it's miles per 1 hour. So this is 64 miles in every 1 hour. There's still those 2 quantities we are comparing, the 64 and 1 in that situation. And same with F. The 1.5 grams of fat is per 1 serving. So it's 1.5 grams to 1 serving. And thus all of the others really are comparing 2 quantities. Now of the ones that were ratios, it's important to realize that there are 3 different types of ratios that we can consider. Part-whole ratios, part-part ratios, and rates. So pause the video and see how you would label the 5 remaining ratios here. Okay, well here's what they would be labeled as. In section A, or letter A, that'd be an example of a part-whole ratio. 7 out of every 10 people prefer McDonald's. And in this one, it's the part-whole ratios that truly are fractions. Because if we say 7/10 of people prefer McDonald's, that is true. Part-whole ratios are fractions and can be used interchangeably. But when we look at B and G, these are called part-part ratios. For example, look at G for a second. For every 2 dogs, there were 3 cats. Neither of these are the whole, right? These are just 2 parts. And if I said, well, 2/3 of the animals are dogs, that would be incorrect. Or 2/3 are cats, that's incorrect. The fraction 2/3 doesn't have a meaning here in this scenario. This is where this ratio does not work as a fraction as we've been used to. It's just 2 to 3, or 2 over 3, or 2:3. It is a part-part ratio. And same with B about the odds of picking a heart. 1/3 of the cards are not hearts. 1/4 are hearts. But again, 1 to 3 is a part-part ratio between hearts and the 3 other suits. And then D and F are our rates. These are ones we're talking about rates of different kinds. Miles per hour, grams per serving. And rates are a very important type of ratio that we use in real life all the time. So take a second. Here's a little fruit basket with apples and pears. Take a second, pause the video, and write down a few ratios that you could write to describe this situation. All right, well, there's many things you may have written down, but let's take a look. Maybe you decided to write a part-part ratio, where we could say, 3 pears to 6 apples. That's 3 to 6. And again, we can simplify ratios like we did fractions. We just have to think about the context and the meaning. In this case, if we simplify it to 1 to 2, it just means for every pear, there are 2 apples, which we can see clearly in the picture. This is a part-part ratio. As a reminder, these are different than fractions. For example, half of the fruit is not pears, half of the fruit is not apples. So it doesn't work as a fraction. It's a ratio. For every 1 pear, there are 2 apples in the fruit basket. We may have also chosen to look at part whole ratios, not while ratios. In this case, we might say there's 3 pears to 9 total pieces of fruit. So 3 to 9. 3 out of 9 pieces of fruit were pears. In this case, if we simplify it, we do get 1 to 3. And in this case, it works like a fraction. I mean, a third of the fruit basket is pears, which makes sense because our beginning meaning of fractions was part whole. And so here, ratios that are part whole operate the same as fractions. All right. Well, I think it's good for us to work our problem-solving skills. So take a moment. I want you to pause the video, and I want you to try this interesting ratio problem. So on the screen, we have 2 pitchers of lemonade that are being made with cups of water and cups of lemonade concentrate mix. The question is, which pitcher will have the stronger lemony flavor? The first one on the left or the second one on the right, or will they be the same? So pause the video and see if you can use some ratios and thinking to answer which one will be stronger lemon flavor. All right, so let's take a look. I'm going to pull up my document camera for a second, and let's take a look. Let's start by examining the situation using a part-part ratio and to think about this scenario. So in the first picture on the left, there were 3 cups water to 2 cups of the lemonade concentrate. And in the picture on the right, there were 4 cups water and 3 cups of the lemonade concentrate. Well, thinking about ratios, again, it means that if we think about this in terms of a set relationship, well, we could scale these up and keep the lemonade flavor the same, depending on the ratio. For example, if we double the amount of water, we'd have 6 cups, and we could double the amount of lemonade mix, that would be 4 cups of lemonade mix, and that would be the same lemony flavor. Or going back to the first one, I could triple that to get 9 cups, and triple this to get 6 cups, and all of these would result in the same ratio or the same lemony flavor. On the other side, maybe I could double pitcher 2 to get 8 cups of water and 6 cups of lemonade mix. And if you notice, here, once we can compare things that have the same, have a constant, they each are being made with 6 cups of lemonade mix, we can see that this one here would have had 1 cup less of water. So because it has less water, this one would have the more lemony flavor. Yum. But of course, we could have looked at this question with a part-whole ratio, right? So for example, in the first picture, there was 3 cups of water, but in total, there was 5 total cups of stuff in the pitcher, water and mix. And the second one, there was 4 cups water out of 7 total cups of stuff in the pitcher. And like before, using ratio thinking here, we can find an equivalent ratio by thinking about, how could we compare these to be similar? Maybe, again, I could multiply these by 7, and if I multiply each by 7, I have an equivalent ratio that would be the same kind of ratio of water to lemonade. And I can do the same over here, except multiply by 5, and I get 20 over 35. Now again, now that I'm comparing pitchers that have the same amount of total stuff in it, I can see that this one, again, has 1 less cup of water. So this one would have more strong lemonade flavor. So it is more lemony. So, is that what you got? All right. So just an interesting little question there about lemonade. All right. Well, let's talk a little more about ratios here. Here's a scenario on the screen. Tom was working a job for $10 an hour. Michael was working a job for $20 an hour. Woohoo! Each got a raise. Tom now makes $15 an hour. Michael now makes $25 an hour. Who got a bigger raise? What do you think? Well, interesting. Bigger in this case might be a bit ambiguous, but this is an important concept when thinking about what is a ratio and not, and thinking about properties of ratios. Because there's really two answers to this question. At first, someone would say, well, Adam, they got the same raise. They each got $5 more. You added 5 to each. Yeah, and that would be called additive reasoning, which would be correct with that argument. Sure, it is the same. They each added $5. Additive reasoning. But wouldn't it also be correct to say that actually Adam got a bigger raise? I mean, he was only getting $10, so $5 in comparison to the 10 he was making, that was half of his salary. It's like a 50% raise. And Aaron got $5 raise, but he was making 20 before. That's only a fourth of his salary. So you might argue that by a relative comparison, using multiplicative reasoning, that Adam got the bigger raise. Now, I say this because it's important to note that ratios always, always, always involve multiplicative relationships. So what does this mean in context? So for example, we might have a situation at Kelly's Trucking Company, 4 trucks carried 24 boxes. So for example, if I add 2 more trucks and had 6 trucks, does that mean I would just add 2 more boxes and say 26 boxes? That would be additive reasoning. I add 2 to the one and I add 2 to the other. Would that be a correct assumption? And of course the answer is no. In this case, if we're comparing trucks and boxes, it's going to be a multiplicative relationship, not an additive one that we work with. So for example, if we look at a ratio table, which can be a great visual to think about ratios, is we could think 4 trucks is 24 boxes. And so multiplicatively, if we double that, if we times 2, we'd have to multiply each number in context by 2, giving us 8 trucks would have 48 boxes. A multiplicative relationship. Obviously on the top, we added 4 trucks, but on the bottom, we added a lot more than 4 boxes. These are things that's good to know. We talk about with students the difference of multiplicative and additive situations, but this works as we keep going. For example, we could multiply each by 10 and get 40 trucks as 240 boxes. And all of these are equivalent, ratios that give us a situation. So thinking about that, we're going to talk about this truck scenario, but I want you to start by seeing how many different ways you can find the answer to this question, okay? I want you to pause the video and see if you can find at least 3 different ways to solve the question on the screen, which is how many trucks would be needed to carry 60 boxes. All right, pause the video and see if you can find 3 ways. Go. All right, did you find some? So maybe, there's many ways to do this, but maybe somewhere on your paper you wrote down something that looked like this. And in doing this, you just wrote a proportion, right? A proportion is defined as a statement of equality between 2 ratios. One ratio set equal to another. And in this case, we have trucks over boxes and trucks over boxes. It lines up well with the context of the story. Labeling units is very important when dealing with proportions to make sure that we are matching the right numbers with the right numbers, and also that we don't lose the meaning of the problem while we work things out. But it's important to note there's more than one way to write a proportion. It doesn't have to look like the way on the screen. For example, I could compare trucks over trucks with boxes over boxes as long as they are in the same order of the first scenario over the second scenario, and that would be fine as well. So, let's think about it. So maybe you did this, and how did you solve it? Well, in our textbook, they talk about different ways to think about ratios and proportions. And one way Van der Waal talks about is working within ratios. Within ratios is kind of working within just the left side or the right side. And for example, on the left side, I can see that from 4 to 24, it's the multiplicative relationship where I times by 6. 4 times 6 is 24. So on the right side, I should be able to do the same thing. 10 times 6 would be 60. And that should be the answer. Now, this type of thinking is very helpful when using a unit rate approach. A within ratio says, okay, well, if I have 4 trucks carries 24 boxes, if I think about that relationship, I can simplify that ratio and realize that 1 truck must carry 6 boxes. and that's a unit rate. So again, if I have 10 trucks, I can multiply it by 6 and get 60. So that's a little different than thinking about between ratios. Between ratios on the right side of your screen is when we are using the relationship across the equal sign from the two different ratios. For example, on the top, if I compare 4 trucks to 10 trucks, I might realize, okay, I more than doubled the trucks, but I didn't triple the trucks. And I might realize, oh, 10 is actually, if I think that's 4 times 2.5 is 10. So that means to get the boxes, I should be able to multiply 24 by 2.5. This type of thinking is often called a scale factor approach. And in my slides, let me just fix this for a second because I think I copied and pasted this. But just to be clear, this should be a between ratio. Okay, there we go. All right. So it would be a between ratio is helping for thinking of scale factors. Again, as I just said up top, if we think about across the numerators, we have 10 trucks compared to 4 trucks. And if I simplify that, 10 over 4 would be 2.5. So again, I can multiply across the bottom at 2.5 and also get 60 to get my answer. So again, when you solve the truck problem, maybe you use some of that type of thinking, a unit rate or a scale factor. But there are many other flexible ways to think about this, so let's just mention a few. One of them might be a ratio table, which again is a great visual for working with ratios and proportions. So for example, we started with 4 trucks with 24 boxes. In a ratio table, as long as we keep that multiplicative relationship, we can try and multiply or divide these numbers by the same thing to think of an equivalent ratio. For example, we know that a unit ratio is helpful if we can get down to 1, so maybe we divide the top and the bottom by 4. That works nice, and we end up getting 1 truck is 6 boxes. But then again, our goal was to get to 60 boxes. So to do that, I'd have to multiply the bottom by 10. So I'd have to multiply the top by 10 as well. And this can be used in a lot of ways. You could divide by 2, you could multiply by 2. It's a flexible way to kind of reason about a relationship and to solve some of those proportion questions. We've talked about model drawing or tape diagrams a lot in this class as well. And again, this is another helpful way to visualize these. We might think about drawing out a rectangle and breaking it up into 4 pieces for 4 trucks and just labeling it. Those 4 trucks have to hold 24 boxes. So if we partition it and divide it equally, 24 divided by 4, we would get that there's 6 boxes in each truck. And, right, so therefore, 10 trucks times 6 boxes in each would give us that correct answer of 60. So model drawing, and with different proportion questions, the model drawing may look different. Sometimes we're going to have 2 different bars going on if we're comparing 2 different things, but just don't forget about that option. And lastly, I bet some of you in your work may have done cross products somewhere along the way, something that we tend to learn a little more in middle school and something we start relying on. But I want to be careful again, not to rely on tricks without thinking about why it works. I know this equation is a bit different than what I gave you. I think the unknown was in the other place, but we're going to use this one just for the sake of this example. What you may have done if you did cross products is you just multiply the diagonals, right? 4 times 60 equals 24 times x, and solve this out for x by simplifying and dividing and getting the answer. Now, one thing to note is sometimes when kids are first learning proportions, we haven't solved equations that much yet. And so again, sometimes this is a skill done later, but also it's a bit magical. Many people don't know why that worked. What happened there? And as always, we like to lean on things that make sense, which is why usually we start with unit rate and scale factor or ratio table or model drawing type situations before we get to the faster strategies or tricks that might be hard to comprehend. So let's see why we do this. Why can you multiply diagonally like that? Well, the secret is just equivalent fractions. I mean, basically, if we start back with where we started, these are hard to see if they're equal because they have different denominators. So how would we get them to have the same denominator? Well, couldn't we just find a common denominator by multiplying each other by each other, like this? Yeah, that would do it, because each side's being multiplied by a giant 1, and we now have a common denominator of 60 times 24. But because we're just trying to set them equal, that means we really don't have to worry about the denominators, right? it's 14 over 40, but those aren't really needed because all I care about is making the numerator the same at this point. And so that jumps us back over to the cross products, which is what the cross product did. So the cross product is just a shortcut for finding common denominators by multiplying each side by a giant 1. And that's why that works. So just a little note on that. All right, a new question for you. Take a moment, pause the video, and try this problem. The ratio of boys to girls at a party was 3-2. There were 35 students at the party. How many were boys? All right, pause it, give it a shot. Okay, well, let's see. Let's suppose that I had a student who solved this question, and they did it like this. Is this correct? Let's think about it. So they said the ratio of boys to girls was 3-2, and there were 35 students at the party. So we see that in the proportion, and we see a variable on top, and they solved it and got 52.5 boys. Something doesn't seem right here. In fact, this is not right. Let's take a look at what happened. Oh, on the left side, the ratio, they wrote the 3-2 ratio, and that was boys to girls, but the 35 was for total students. So on the right side, the ratio was boys over total students. See, we can't do that. In a proportion, we have to line up the same units with the same units. This would not be a correct proportional statement, so we're going to get an invalid answer. Interesting. So the left side we see was a part-part ratio, boys to girls, but the right side was actually a part-whole, 2 different ratios here. A note on this is, just as always, labeling units is so important to keep sense-making alive. So as teachers, let's model that by labeling units with students. 3 boys over 2 girls equals X boys over what? Wait, we can't do 35 students, right? So label those units. So let's take a look at some ways to think about this. Well, what we might do is we might choose to use, we could use a part-whole ratio on each side. For example, on the left side, instead of 3-2, we could say 3 boys out of every 5 kids, 3-5. That would look like this. 3 boys over 5 students equals some number of boys over 35 students. And that would be a correct proportion. And like we saw earlier, without using cross products, you could do this in a variety of ways. One, within ratio, we could just look at the ratio. When you use a part-whole ratio, that means 3/5 of the students are boys. So basically, we know that we can just take 3/5 of 35. 3/5 times 35 is 21, and that would be the correct answer. Although personally, I would prefer to use between ratio thinking, because when this one, I can look across between the denominators and realize, oh, I see a multiplicative relationship. I just multiply the number of students by 7, which means the top has to have the same relationship. So I can just multiply the number of boys times 7, right? And 3 times 7 is 21. So that would be my preferred strategy, because I like that. That's clean and works well with the between ratio thinking in that case. More of a scale factor of 7, going through. Now, just a note again, just want to make this clear, is that when we solved the question before, I set it up like the left, boys over students equals boys over students. But again, there are many right ways to set up the same proportion. So if you or your students set it up like this would also be fine, as long as we're consistent with lining up the scenarios with each other. But this would also be a correct way to set it up, and we could still use, the within or between ratio thinking. Well, so this is a big idea, but I want to emphasize the idea that proportional reasoning, like the idea of equivalence, is considered a unifying theme in mathematics. It's at the core of many important concepts that start, in later elementary grades and continue on for all future mathematics. But when you think about ratios and proportions, just some ideas that may come to mind are things like slope, the ratio of rise over run, speed, we have distance over time, lots of rates, words per minute, percents, we're looking at something out of 100, pi, the ratio of a circle's circumference over its diameter. We have probability, trigonometric ratios, density, and much, much more. And so I just stress this, knowing that these ideas are such important foundational ideas that will pay dividends in the long run as kids learn to really be flexible and understand them deeply. So with that, that concludes our lecture on an introduction to ratios and proportions. So until next time, keep doing that math.